Hello. So in the last session we discussed about the analysis of T-beams, or you can say flange beams, and in that session we covered three cases in which the analysis of a flange section is to be done. The first case that we discussed was neutral axis was in flange, that is XU is less than DF. The second case that we discussed was that neutral axis was a limiting section or a appellant section. That means FC is equal to FT and XU equal to DF. Now the third case that we discussed was the neutral axis was in web section. That means XU is greater than DF and FT, that is a tension force, is greater than the compression forces. Okay? So in this session we will be seeing furthermore twisted numericals regarding our analysis problem, and then we will be starting with our design problem, that is how to calculate the area of steel for a T section or a flange section. We will be seeing that. Okay? So starting with our today's session, the first question here is find Cmax, Tu and Mu for a RCC T-beam having following dimensions. That means first we have to know what does we have to find out. That means what is this Cmax, Tu and Mu. So Cmax is the compression force, that is the maximum compression force, or in the other terms we can also say that Cmax is the value of Fc that we already know how to obtain. So Fc, that is our compressive force, that is nothing but Cmax. Tu is our ultimate tension load, or you can say the maximum tension force. So this Tu is again nothing but the value of our Ft, that is our tension force, and Mu is the moment of resistance. So we are supposed to find these three things for the following criteria that are being given. So the depth and width of flange, that means this 100 mm is the depth of flange, that is df. This 900 mm is the width of flange, that is bf. This width of web and effective depth, that means this 250 mm is the width of web, that is bw, and this 550 is the effective depth, that means small d. Clear? So the steel that are to be provided is given as 4 numbers of 25 mm diameter. So 4 numbers of bars are used of 25 mm diameter. So from this the value of AST can be easily obtained. The grade of concrete that is to be used is M20 and the grade of steel that is going to be used is Fe415. So we'll be starting our numerical problem. So first, the area of steel. So area of steel, as 4 numbers of 25 mm diameter bars are given. So area of steel AST will be 4 into pi by 4 25 square, or you can directly solve this from your steel table. So this answer comes out to be 1963 mm square. Now our first step to solve any analysis problem will be the comparison between our compression force and the tension force, that is to compare our Fc and Ft. So Fc, that is our compression force, it is also the value of Cmax. So our first case is completed here. Fc, that is 0.36 FCK BF DF. FCK is the grade of concrete, or you can say the strength of concrete according to the grade. BF is the width of flange. DF is the depth of flange. So solving everything, all the parameters are given in the question. So solving everything, we are getting 648,000 Newton. This is the compression force that we are getting. Now moving on to the tension force. So tension force in whatever chapter we deal with or whatever topic we deal with is always equal to 0.87 FY/AST, because it depends upon the steel bars. Clear? So 0.87 Fy. Fy is the strength of steel bar or the grade of steel that is being used. So in this case Fy will be 415 Newton per mm square. AST is the area of steel bars. We have already obtained it to be 1963. So solving everything, we are getting 708,741 Newton. Now our basic fundamental thing is to find the relation between Fc and Ft. So from these two values we can easily say that our Ft, that is tension force, is greater than the compression force. Okay? So as the tension force is greater than the compression force, that means the neutral axis will be shifted towards the tension zone. And as we all know that tension zone is in the web portion So neutral axis is in web, we can easily say this, clear. And again, as neutral axis is in web, that means the depth of neutral axis will always be greater than the depth of flange. So XU greater than DF, this condition is automatically applicable if the neutral axis is in web, clear. So now we will be proving whether this condition is actually going to be satisfied or not. That means we have to find the value of XU because DF is already given in the question. So we will be finding the value of XU and then we will be seeing whether this statement or this relation actually follows or not. So for this condition, that is whenever we are getting neutral axis in web portion, then the value of XU can always be obtained from the equilibrium condition. That means to find the value of XU, we will be always using this equilibrium condition. That is, compression forces are always equal to the tension forces. But as we are talking about flange sections, compression forces are divided into two parts. That is, C1 is the compression force due to the vertical web section, that is our behavior according to the singly section, and C2 is due to the flange portion. And the value of C1 or the equation for C1 will be 0.36 FCK BXU. Now the question arises that we have two widths, that is width of flange and width of web. So which width is to be substituted here in this portion, and that all depends upon the position of the neutral axis. Okay? So we are always calculating the position of the neutral axis. Here in this particular question or in this particular answer, we are getting the neutral axis to be in web. That means the web portion is the governing criteria. So the width will be considering of web. Yeah, so wherever the neutral axis passes through that sectional area, we will be considering the width. So here we will be substituting BW. XU will be our unknown. 0.446 FCK, BF minus BW into DF. This is our C2 force, that is compression force on the secondary portion. And this is our tension force, that is 0.87 Fy AST. So in this whole equation, the only unknown is our value of XU, and XU we are getting it to be 69.75. The value of XU is obtained as 69.75, but this 69.75 is less than 100 mm because the depth of flange is given in the question to be 100 mm and we are getting XU less than DF, which is not applicable, or that is not okay. Why? Because the neutral axis is in web, so it must be proved that the XU value is greater than DF, but according to this equation, the term that is XU is coming out to be less than DF, which is not possible. Clear? So we have to recalculate it again. And how we will be recalculating it again? We will be using this condition. That is, we will be substituting this term that is given in your IS code, page number 97. On the right hand side top, you can see an equation for YF being mentioned. So YF is equal to 0.15 XU plus 0.65 DF. This is the equation for YF, and YF is nothing but the effective depth of flange. So here in this equation, that is the equilibrium equation, we will be substituting the term DF. DF is the total depth of flange. We will be substituting this term DF by YF. Clear? So whenever you are getting this condition in which the answer comes out to be in neutral axis, but the value of XU comes out to be less than our DF, in that condition we will always substitute the term DF by YF in this same equation. So now we will be finding the value of XU again by replacing this DF by the equation of YF. So first we will be looking onto the equation of YF. So YF, the equation as mentioned on page number 97 of your IS 456-2000, it is 0.15 XU plus 0.65 DF. So we can say that the YF equal to 0.15 XU. XU is our unknown, and DF we already know that is 100 mm. So plus 65. This is the equation of YF that we will be substituting here, that is in the parameter of DF. So solving it again, that is C1 plus C2 equal to T. This DF now will be substituted by this YF. So the final answer of XU here comes out to be 122.68. Clear? The answer comes out to be 122.68, and now this value is greater than 100 mm. So as it is greater than 100 mm, it is perfectly okay and the neutral axis is in web. Clear? So now after confirming the position of neutral axis, we will be proving the section, that is whether it is under reinforced, over reinforced or balanced. For that we will be finding the value of XU max. XU max can always be obtained from page number 70 of your IS code. The ratio for Fe415 steel is 0.48 D. So solving it, we are getting XU max to be 264 mm. So as the XU is less than XU max, it is a under reinforced section. Yeah? Now we will be focusing on our third parameter, or the third question that was asked, that is to find the value of mu, that is moment of resistance. So to find the value of mu, the case that is possibility is our G2.3, because the neutral axis is in our web. So as we can see here, G2.3 on page number 97, it is mentioned for XU max greater than XU greater than DF. So this condition is satisfied. XU max comes out to be 264, XU was 122 and DF is our 100. So whenever this condition is satisfied, then we can use our G2.3. So this condition is now satisfied. So the moment of resistance, that is mu, may be calculated by the equations given in G2.2, but when the DF by XU ratio does not exceed 0.43, does not exceed, that means it can be less than or equal to. So whenever we are getting the relation that the ratio of DF by XU is less than or equal to 0.43, then we will be using the equation for mu, that is belonging to G2.2, that means belonging to page 96. Clear? And we will be using G2.2.1 when DF by XU exceeds 0.43. That means whenever the ratio DF by XU is greater than 0.43, then we will be using the equation G2.2.1, which is visible here. Clear? G2.2.1, which is this equation that is given on page number 97. But this is the most important thing to remember, that in both the cases, that is whether the ratio is less than equal to 0.43 or it is greater than 0.43, in both the cases we have to substitute the term XU max by XU. Do not forget that. Clear? So now we will be finding the ratio. So the ratio DF by XU, DF is 100, that is given in the question. XU we have calculated it to be 122.68. So this ratio comes out to be 0.815, which is greater than 0.43. So as it is mentioned that when this ratio exceeds 0.43, we will be using the mu equation that is given in G2.2.1. That means this equation we will be using. Clear? So this equation that is we will be using for page given in page number 97. So using this equation, but always you remember that we will be substituting the term XU max by XU. So this equation, that is mu equal to 0.36 XU max by D, 1 minus 0.42 XU max by D, FCK BW D square plus 0.445, or you can say 0.446 FCK BF minus BW into YF D minus YF by 2. In this whole equation, we have to substitute the term XU max by XU. So solving it, we are getting an answer 358 into 10 raised to 6 Newton into mm, or you convert it into kilonewton meter, then it comes out to be 358 kilonewton meter. So this is how you will be solving the moment of resistance sums when the third case, that is neutral axis, is in web and the criteria of XU greater than DF does not satisfy. Clear? So now we will be starting with our design problem. So here the question for design is calculate area of steel required. That means we need to find the value of AST. So calculate area of steel required for factor moment of 450 kilonewton meter. Now, as we discussed earlier, that this statement is very important, that whenever it is given that the moment or load is factored, that means there is no need to multiply the given load or moment by the factor of safety. So whenever we are obtaining these three words or either of these three words in the question, that is either we are saying factor, either we are saying the design, or either we are saying ultimate, out of any these three words, if you are seeing any word given in the question, then there is no need to multiply the given load or moment by 1.5, that is the factor of safety. So here it is mentioned that it is a factor moment of 450 kilonewton meter, so there is no need to multiply this 450 by 1.5. For a T-beam having following requirements, that means the data is being prescribed, the width of flange, that is BF. So BF is given as 1250 mm. The depth of flange, that means DF. So DF here it is mentioned as 100 mm. The width of web, that means BW. So BW is mentioned as 250 mm. And the overall depth, that is capital D. So capital D here it is given as 600 mm. Effective depth is given as 550 mm. So according to this, cover will be 50 mm. Overall depth minus effective depth, that will be our effective cover. And it is also said we have to use M20 concrete and Fe415 steel. So now the basic of finding the area of steel, that is we need to find the AST term. Now AST can be only obtained from this relation of our moment, that is according to the equation for moment. Now as we all know, the basic equation for moment is force into perpendicular distance. We will be using the same equation to find our answer, that is force into perpendicular distance. But for a flange section, we know that there are three forces, C1, C2 and T. C1 is 0.36 FCK BXU, whether it can be of flange or whether it can be of web, depending upon the neutral axis. C2 is 0.446 FCK BF minus BW into DF. And T, that is a tension force, is 0.87 FY AST. So out of these three forces, the only equation that has AST in it is our capital T, that is tension force. Clear? So we will be using that tension force into the equation for moment, that is when moment equal to force into perpendicular distance, we will be using a tension force and the lever arm will be our perpendicular distance. So the moment is already given, so we will be focusing on the term of lever arm. So lever arm for a flange section will be represented by Z, and Z will be always equal to D minus DF by 2, that is effective depth minus depth of flange by 2. Effective depth is given in question to be 550. The depth of flange is 100. So the lever arm here comes out to be 500 mm. Okay? So now we will be using the equation for moment. So MU, that is force into perpendicular distance. So force, that is a tension force. So tension force is 0.87 FY/AST. Fy is the grade of steel or the strength of steel, and strength of steel is according to our Fe415, that is 415 Newton per mm square. And Z is a lever arm. Lever arm we have already calculated it to be 500. So MU, as it was 450 kilonewton into meter, we will be converting it into Newton into mm, because the other parameters are in Newton and mm. So 450 into 10 raised to 6, 0.87 into 415, that is grade of steel, and multiplied by AST multiplied by 500. 500 is our lever arm. So in this equation, the only unknown is the value of AST. So solving it, we are getting AST to be equal to 2492 mm square. That means the area of steel required is 2492 mm square. Now whether we are solving a singly reinforced, a doubly reinforced or a T-beam, after calculating the area of steel, we must provide the number of bars. So the next step will be the provision of bars, and provision of bars can always be obtained from our steel table. But there are two possibilities. One first possibility is that you can provide homogeneous bars of the same diameter, and the second is you can provide composite bars. Composite bars or composite reinforcement. That means providing bars of two different diameters. It is up to you what the type of bars you select. That is, either you are going for homogeneity or you are going for composite. Here, according to our page number 71 of the steel table, you can directly see from table 20 that the relation between the diameters and the areas are prescribed. So the AST required, that is the area of steel required in our case, is 2492 mm square. In steel table it is mentioned in centimeter square, so we will be converting this mm square into centimeter square. That comes out to be 24.92 centimeter square. So we will be focusing on an area from this table that is greater than 24.92 centimeter square, and do not provide greater than 6 numbers of bar, because if we provide greater than 6 numbers of bar, then it is not possible to provide in a single line. Clear? That there may be consequences regarding that. So we will be selecting the number of bars to be maximum 6. So in this case I have opted for a composite reinforcement. You can provide homogeneous bars, there are no issue in that. So I have provided 4 numbers of 28 mm diameter and 2 numbers of 12 mm diameter. 4 numbers of 28, that means if we look upon this, then this 28 and 4 numbers, that means 2463 mm square, and 2 numbers of 12, that means here 226. So if we add these two, then we will be getting the total AST. So the total AST is 2689 mm square. The required was 24.92. We have provided 26.89. So the provision or the requirements is fulfilled and the steel criteria is completed. So basically our entire sum is finished here, but now we have to prove whether we have provided the correct amount of steel or not. For any design problem, checks are mandatory. Clear? So our entire sum is finished here, but now we will be checking whether we have provided correct answer or not. And check is basically the analysis problem on whole in soul. Clear? That means again we will be solving the entire analysis problem. So now analyzing this AST, the first case is the relation between FC and FT. So FC from this equation, that is 0.36 FCK BFDF, and FT can be obtained from 0.87 FI AST. Here we will be using the value of AST provided, not required. Keep that in mind. Here we will be substituting the value of AST provided after finalizing the number of bars. So here FC comes out to be 900 into 10 raised to 3 Newton, and FT comes out to be 970 into 10 raised to 3 Newton. So clearly it is visible that the tension force is greater than the compression force. So as tension force is greater than the compression force, the neutral axis is in web and XU should be greater than DF. So now we will be focusing on this parameter, that is whether in actual circumstances is XU greater than DF or not. So DF is already given in the question to be 100. Now we will be finding the value of XU. XU can always be obtained from the equilibrium condition, that is compression forces are equal to tension forces. So solving it, C1 plus C2 equal to T. From this equation the value of XU can be obtained as 38.88 mm. So the XU here comes out to be 38.88 mm, but it is less than 100 mm. Clear? And as 100 mm, that is the depth of flange. So this condition is not satisfied. That means according to our understanding, that is whenever we are getting neutral axis to be in web, XU should always be greater than DF. But here we are getting XU to be less than DF. So in this scenario, what we will be doing? We will be substituting the term DF by YF in the equation of our equilibrium condition. Clear? So now we will be finding the value of YF. YF, the equation is 0.15 XU plus 0.65 DF. This equation is given in page number 97 of your IS code. So solving this, we are getting the term that is YF equal to 0.15 XU plus 65. So now in place of here DF, we will be substituting the term YF. So solving it, we are getting XU to be 122.22 mm. Now this XU is greater than 100, which was DF. Clear? So our actual criteria are satisfied. So the XU that we will be using in our entire sum now will be 122.22. Now we will be finding the relation between XU max and XU. XU max here comes out to be 264 mm. From page number 70, XU max can be obtained and it is under info section. So this criteria of G2.3, that is XU max should be greater than XU, should be greater than DF, is satisfied, and now we can use the relation. So moving further on G2.3, it is mentioned that the ratio of DF by XU is important. So we will be finding the ratio of our DF by XU. DF by XU here comes out to be 0.81, which is greater than 0.43. So as it is said, we will be using G2.2.1 when DF by XU exceeds 0.43. Clear? So we will be using this equation that is given in G2.2.1 of page number 97. So solving it, we are getting our XU, but keep in mind we have to replace the term XU max by XU. Clear? So here substituting everything in the equation that is given in page number 97, we are getting MU equal to 490.93 kilonewton meter. Now the main thing is that the question was not to find the value of MU, it was to find to calculate the amount of steel. We have calculated the amount of steel and now we are proving whether we have provided the correct amount of steel or not. So after finding the value of MU, the statement should be compulsory and mandatorily be written that the maximum capacity or the maximum moment that this steel bar can carry is 490.93, and the maximum that was asked in the question was 450 kilonewton meter. Okay? So as this answer that we obtained is greater than 450 kilonewton meter, that means the AST that we have provided is correct. This statement is must whenever design problem is asked. Clear? So this will be our today's exercise problem. Do solve it, because from now we will be starting with our design portion of our flange beams, and in the next session we will be discussing further more design numericals. Thank you.